Welcome back from lunch. My name is Craig Abramson. I'm going to do a session today called FPGAs for Highest Performance Inference, which is a neural net term. I am from Xilinx. I am based out of Longmont, Colorado. That's a picture from the parking lot of our building. Kind of nice. I am a senior technical marketing engineer. I've been that for a couple years. Prior to that, I was a middle-aged technical marketing engineer. Nothing. Okay, I promise that's the only joke I will try and tell. All right, we're going to talk about machine learning for the next 25 minutes. And here's how we're going to do it. We're going to talk about FPGAs just in general to kind of level set, because I noticed here in this particular venue, in this particular conference, not everybody knows what an FPGA is, so I'm going to have a slide or two on that. And then we're going to talk about things that influence the decision to use an FPGA and neural nets. And then we will conclude with a conclusion, because that's what you do. All right, quiz. FPGAs are, raise your hand if you think it is a flexible parallel GPU accelerator. Nobody? Okay. A functionally pervasive gigaspeed ALU. No? Field programmable gate array. Sweet. All right. And fast processor for GNU assemblers. Someday, yeah. Right now it's a rather slow it's a decelerator for GNU assemblers. All right, so everybody kind of knows what an FPGA is.
I think you were missing E.
What's?
All of the above.
Because sometimes it's that. Sometimes it's that one. Okay, so why might one use an FPGA? They might use an FPGA as an alternative to an ASIC, a dedicated chip. Why would you do that? You get faster time to market, so it takes a lot of time and money and energy to do a full custom chip. FPGAs allow you to iterate and get to market faster. It is a single chip solution versus having multiple different chips with different functions. You can pull all of the different functions together and have a single chip, which is a lower power, often higher reliability solution. It is reprogrammable, so you can be a very sloppy, bad designer like I was before I went to marketing. And that is a lower risk solution. Oops, there was a fourth one, and I think I got rid of it. And I have to cop to something. I have a little bit of dyslexia, and I thought this class went from 2 to 255, but it really goes from 2 to 225. So I lopped about half of my slides out, and I think subconsciously I'm racing to get through it, and I also had an espresso. So hopefully you'll be able to keep up. Tell me to slow the hell down if you need to. That's okay. In the FPGA world, we do, so okay, we're going to switch gears here. In the FPGA world, we do inference rather than training. Some solutions that are doing neural nets in the world do both training and inference. And what I'd like to do is take a second to kind of explain a little bit at a very high level the difference between training and inference if you don't know. Training in a neural net is where you start out with a neural network and imagine it's like a blank brain and you're trying to teach this thing what dogs look like. You show it a zillion pictures of dogs and it eventually trains itself to recognize dogs. And that takes a lot of math and a lot of energy and a lot of time. But once you have that neural net and it's been trained to recognize dogs, you can then figure out which parts of the neural net were important, get rid of the things that weren't, and then it becomes a much smaller job to infer what a dog is from all the training data you've done. And you can then run a much more efficient, lower power type implementation of this neural net. And I like to use the example, it's kind of like riding a bike. So if you think back to when you were first learning to ride a bike, you were throwing all of your attention at it. You were making sure that you were balanced. You were looking at the cars coming. You were looking at the ground, hoping you weren't going to hit it. You were using a lot of your brain power to learn to ride the bike. And you probably figured it out. And now if you were to ride a bike, you would not probably use very many neurons at all. It's very similar in training and inference. So that's my example of how to distinguish between training and inference. And again, in the FPGA world, we do inference and we don't do training. And there's like subtle exceptions to that we're not going to cover in 25 minutes. All right, so one of the reasons FPGAs are useful in AI and in inference is it's solving a problem called the rate of AI innovation. And what that means is AI is changing fast, okay? And to illustrate the point of why FPGAs make sense in AI, I'm going to do a little step back in time and think about PCI Express as it has rolled out over the years and years since like the year 2000, et cetera. And so I used to be a field applications engineer, and I called on a test and measurement company, okay, that shall go unnamed. And they made PCI Express analyzers. Now, if you think about PCI Express, the PCI Express standard spec is not ratified, it's not ratified, it's not ratified, and then all of a sudden it is. Now, all of this time when it's not ratified, it's changing and thrashing a little bit, but my test equipment company really wanted to come out with a product that could be a PCI Express analyzer at day one when that spec was available. So instead of making a chip that they took their best guess on, a custom chip that they took their best guess on how PCI Express was going to work, they used an FPGA instead. So the whole time as the spec was changing, they would track those changes, and then on day one, when the PCI Express spec was solid and ratified, they had a product ready to go. Okay, so everybody kind of follow that kind of thing? So this is an example of neural nets and the AI landscape. It's changing a lot, much like the PCI Express spec might have been changing over time. So one of the big places it's changing right now, and this is just one example, again, it's a 25-minute talk, so we can't go in a whole lot of detail, but one of the places that it's changing is in the precision landscape. So when you're doing training, like I said, you're doing training in like FP32 and very high dynamic range variables and things like that, because you have to do a lot of math and accommodate for all the different things. But there's a lot of research going on that's trying to figure out in the inference realm whether you can get away with not FP32, maybe a floating point 16 unit that's got less dynamic range, or even integers. And in fact, that's a very active area of research, and we take advantage of that. My point being that as these algorithms change and the precision has to change, we can accommodate that in an FPGA very, very easily compared to some of the other alternatives like a GPU, which I'll talk about more in further slides. GPUs have a fairly fixed architecture, so if you want to use a lower resolution, you can, but it affects your throughput and your performance of your design. So inference moving to lower precision is one example of why FPGAs make a lot of sense when you're doing neural nets, because the precision that you're going to need could very much change over time because there are so many changes going on in the neural net industry. You guys keeping up with me? I feel like I'm talking fast, but I'm also watching my clock here, and it's ticking away. Okay, so that was the fact that things are changing. That's one of the reasons you might want to use an FPGA when you're doing a neural net. The other one is performance at low latency. FPGAs do very well. Let me restate that. FPGAs implementing neural nets have very low latency, and low latency is very important in a lot of neural net applications. For instance, let's say you're driving a car and you've got a bunch of cameras around your car and it's doing some obstacle avoidance kind of thing, and maybe one of those obstacles was a pedestrian. If that system has high latency, it can struggle to identify the fact that there is a pedestrian there before you actually hit the pedestrian. So latency is a very key concept. Looking at it differently, latency is how long it takes from when information first enters the system to when you get useful information out. So here's kind of a high-level roadmap looking thing that explains why a GPU type system has latency associated with it. So a GPU is used with a CPU, and the way the whole thing works is the CPU has to pull, here I'll just use this. CPU's got to pull instructions out of DRAM, it's got to run it, it's got to get it through the cache, it's got to execute it, it's got to put together a kernel that it's going to then deploy over PCI Express or AXI, depending on whether it's a SoC or in a data center. It's got to load the instruction into DRAM. The DRAM, the instruction executes, and the instruction says, all right, so let's pull the image out of DRAM and load it into all of these ALUs. And all of that equals, and it's got to load a lot of ALUs to get the performance out of it. All of that equals latency from the time where you start the execution all the way to the time where it's ready to operate on all of the data that's been loaded into the ALUs in the GPU. That's a good deal of latency, and that's just something that's fundamental to a GPU architecture. Because if you think about GPUs, you know, their mission in life, where they really started from, was they were designed to operate on images, which is a whole lot of pixels operating in parallel. Whereas, you know, that's great for images, but it's not really great for getting low latency. On the FPGA side, oh, let me go back. So the way GPUs work around that is they do a thing called batching. So if you go ahead and you execute your instruction and you load one image into here, you can do your part where you load the instruction, move it over here. It says, hey, get me an image. It gets the image and then chunks it through. That can happen in some amount of time and it's okay. But what they really do to try and hide the latency is load as many images up as possible, and they call that batching. So if you're ever looking at specs, you might see something that says how big the batch size was on the GPU. So batching is another way of saying, hey, we're trying to hide the latency in this batching. So we're setting it up to do, it's kind of like a DMA transfer. It's like, all right, well, we're going to transfer a whole lot of data and we'll suffer through the overhead at the beginning. That's kind of what batching does. On the FPGA side, we kind of don't have that concept because we get, it's programmable hardware, so we get to set that up however we want. So what we do is we have the image or whatever data it is that you're going to be running through your neural net in external memory. We pull it into memory that is local to your hardware neural net accelerator, and then we just kind of chunk it through. So in FPGAs, like I say, we don't have a batching type of a problem. We just run it through in a pipeline fashion, so much, much lower latency in that scenario. So there's another thing we do, and I talked about this before, and that is once you have your trained neural net, there's a lot of ways to make that network simpler. And a few of the things that we do are something called pruning and compression. So if you imagine you've trained your neural net and it comes out and it looks like this, it's a bunch of fully connected neurons. It's a bit of a simplification, but a lot of fully connected neurons running floating point math and things like that. What ends up happening when you have something like this and you're actually doing the processing that is associated with neural nets, you get a lot of matrices that are fully populated, and there's a lot of work that has to go into doing matrix math. And what we do is we go through and we analyze the matrices and the values and things like that, and we do something called pruning. We find out which neurons aren't really doing very much, and we either prune them out or change them from floating point to fixed point and change the precision and things like that. And what you end up getting is a more sparsely populated matrix. And that's an area where FPGAs can really excel as well. So if we have a partially populated matrix, there's things that we can do in our neural net accelerators that we've designed that allow you to get higher throughput. So in the GPU world, there are also ways to do sparsely populated matrices, but they don't actually result very much in substantial savings in performance. It's still kind of going through it. It's just handling the fact that it's sparsely populated. So anyway, so we figure out how to prune it. Here's what it looks like. So you'll have things that are less connected, and that just ends up equaling less math. So let's see. So pruning, I think I covered all this. Smaller, lighter networks, less capacity, blah, 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 blah. So yeah, FPGAs are better with smart matrices, single chip. Yeah, these are all the things I said. And we have tools that do this stuff for you. So once you have your trained neural net, you run it through our tools, and it takes care of that stuff. So another thing that we like to talk about in the FPGA world is benchmarks and things like that, because if you look at published benchmarks and just look at the numbers on them on their own, a lot of times it'll look like they like a GPU might have better performance than an FPGA, but you kind of have to look at it in the context of how it's used. A lot of the benchmarks that are out there are just looking at, all right, well, we've got these cores in our GPU, and each one is capable of a thing, and we're just going to aggregate them, and we're going to come up with a number. And that doesn't always tell the story, because architecturally different things might be happening. You can run into things with how easily or hard data can be pulled through the GPU. So if you look at this little thing here, so U200 and U250, those are Xilinx boards, actually, and they have quoted numbers of 18 and 33 teraops, whereas the T4, P40, and P4, those are GPUs, and they have quoted teraops performance numbers much higher, okay? But if you actually run it through, and I like this, it says we put them in focus, and then we actually take it out of focus, so I think that's misleading, but I apologize for that. So what happens, like I said, is these usable tops get limited by various conditions, memory bottlenecks, how the code is structured, whether something has to stall or branch. And then GPUs even do this thing called frequency throttling, which is this fascinating thing where if the power gets too high, it just kind of drops the clock down and you don't always even know about it. So in addition to that, other things affected like batch size, like we talked about before. Whether there's a latency spec in the power, which again goes back to this frequency throttling thing and different accuracy requirements. So cut to the chase. Here's some real benchmarks. This is in this example, it's GoogleNet batch equals 1, because again, we want to have the lowest latency solution. And really, the P4 and the P40, and this is kind of an estimate at this point, but the P4 and the P40 have a much lower throughput images per second, again, for the same batch size equals 1, whereas our U200 and U250 Xilinx solutions considerably higher. So the message here is, and this message actually flies in like all FPGA applications. You really have to look at the system and how it's implemented and things like that. So, focus on the application level performance, and that's where we typically do a good job. Here's another example where we have a speech-to-text conversion. The neural net looks like this. We got a CN. We have these layers here. Each one of these layers got implemented and run through our tools. So we were able to do pruning as needed and things like that. And if you ran this algorithm just in a CPU only, pretty sure it was a Xeon, it takes about that long. CPU plus a GPU, it drops down as you would expect. But CPU, again, with this U200 board, drops down quite a bit more. So you can see an FPGA solution is about twice as fast in this particular neural net, about twice as fast as what a GPU is able to do. And again, batch equals 1, so that's a key thing for us. Wow, kind of ripping through this. Any questions? You guys doing all right? Yeah. Oh, I'm sorry. Yeah. Wait. Got to use the thing.
On that last slide, you were showing the time difference in it. But another thing that would be interesting to show would be the power utilization.
Absolutely.
Because, I mean, it could be 42 milliseconds, and it could be a lot of power from the GPU.
And I don't know the answer for these particulars, but you're exactly right. That's
just a suggestion for next round of slides.
Thank you. Absolutely. Grab it. Here we go. Was there another question? Okay. So another place where FPGAs do well is what we call, I was going to say it's a marketing term, but I'm a marketing guy, so I shouldn't really badmouth myself. Whole app acceleration, really the point there is the fact that the FPGA isn't just doing the neural net. FPGAs are programmable hardware. So let's say you've got some weird sensor that somebody designed that has a non-standard interface. The FPGA can be modified to communicate with that sensor in a fairly straightforward fashion if you're an FPGA guy. If you have, it's an SoC, so it's got 5 serial ports, but you need 25 for some reason. An FPGA can very easily implement the rest of those serial ports. So it's programmable hardware. So the point is, FPGAs do a great job of incorporating your whole application, not just the neural net like we're talking about. So, always kind of think about that. And that's really been our claim to fame. Sometimes we call it, over the years, I've been with Xilinx a long time, sometimes it's logic consolidation, sometimes it's glue logic, but the point is kind of any piece of hardware with some exceptions can be integrated into the FPGA and it becomes a single chip solution. So let's look at some examples of whole app acceleration in the context of a neural net type thing. So this was a company called YY Inc., and they had a product that would read in video, do some analytics to it, and then do some post-processing to that analytics, and then encode it. Anyone want to take a guess? Anybody want to take a guess of what the real application of this was? Okay, so I think, and I should know this, but I think it's one of those deals where somebody uploads a video and it analyzes it and it figures out where the face is and like puts cat ears on it or something like that. I mean, there's a lot of that. That's an incredibly booming business right now. And I think that's kind of what's going on here. Anyway, this company was growing quite a bit. So they were able to do this capability in units of these servers. So they were doing this with 30 of these E5 servers, and these were all, rack size, 19-inch racks. And they were trying to scale that. And what was happening is they were blowing out of the power envelope for the particular, for their facility. So they came to Xilinx to find out if there was a way to get that functionality in a smaller envelope so they could scale better. So we threw some engineering at it, and they ended up getting all of this capability down into a single rack unit. So 48 of these Xilinx devices replacing that. And the way it ended up coming out was 10x energy improvement and 3.3x performance improvement. So better, smaller, faster. I can't speak to cheaper or not, but definitely better, smaller, and faster, lower power. So this is an example of a whole app acceleration that includes a neural net type of a feature. Man, crushing it. All right, so there you go. So we talked about why FPGAs. Why? Because you can integrate logic. You can get a single BOM solution. You can do things better at low latency, and you can do your whole app acceleration. And that's what FPGAs are good at. Is there any other questions or comments?
You talked about performance, latency, power performance. What about price performance compared to GPUs?
I'm not going to lie. I'm not really prepared to talk about price. I don't even always pay attention to that.
Okay.
Any other Xilinx people in the room want to hit that?
Yeah, I mean, it depends on the application, but for lower applications, it turns out to be not much cheaper for the whole system, if you look at the whole system. Okay. Yeah. So sometimes it's cheaper just because of some people that are more thinking about the capex versus the opex, right? When you have that kind of power savings, then you can save it on the opex. But even the capex in many places, the cost, the initial cost of the board and so on. But it really depends on the application. GPUs are good in some applications, and for other neural networks, it's a big difference, and FPGAs are much better. So it really depends on the application.
And just to sort of build on that, one of the advantages that FPGAs bring to the party versus a GPU is this concept of scalability. FPGAs, we have little guys that are like $20 or $30, and we have big guys that are tens of thousands of dollars. In the GPU world, there's fewer price points because there's fewer devices. I mean, there's fewer die, basically. For any one of our FPGA families, and like today, for instance, there's probably 9 or 10 different families that you could design from. Each one of them probably has 10 different devices in it. So there's a pretty broad array of choices you can make of what FPGA you're using. So you can hit a price point. There's perhaps a better chance that you'll be able to hit a price point that better matches your budget, just because we have a range of devices, if that makes sense. Anybody else? We're at 24 minutes and 40 seconds. Awesome. Thank you very much.